Introducing the MRB constant, convergence, geometry, and open problems. The MRB constant, recently introduced by Marvin Ray Burns, emerges from the alternating series of the nth root of n and exhibits deep connections with both analytic number theory and high-dimensional geometry. This talk introduces the constant's definition and its convergence properties, and its geometric interpretation in terms of n-dimensional hypercubes. We also discussed numerical methods for computing the constant, including splitting of the series, asymptotic analysis, and integral representations. Emphasis will be placed on geometry and special functions. The presentation will outline key starting points for further exploration and highlight ongoing collaborative work aimed at formalizing these results within the framework of modern mathematical research. The MRB constant, approximately 0.187859, is a mathematical constant named after Marvin Ray Burns, who discovered it in 1999. The constant is defined as the upper limit of a specific sequence of sums related to an alternating series involving the nth root of n. Its decimal expansion begins as 0.187859, and it is associated with the integer sequence A037077 in the online Encyclopedia of Integer Sequences. See MathWorld, Wikipedia, and marvinrayburns.com. What is the MRB constant? The MRB constant is a mathematical constant named after its discoverer, who published his discovery in 1999. The MRB constant is defined as the upper limit of the partial sums of the sum k equals 1 to n of negative 1 to the k times k to the 1 over k equals s sub n. As n grows to infinity, the sums have upper and lower limit points of approximately 0.187859 and negative 0.812140 respectively, separated by an interval of length 1. The constant can be explicitly defined by the following sums and interval. 0.187859 equals the sum of k from 1 to infinity of negative 1 to the k times k to the 1 over k minus 1 equals the sum of k from 1 to infinity of 2k to the 1 over 2k minus 2k minus 1 to the power of 1 over 2k minus 1, which equals the integral from 0 over 0 to complex infinity of cosecant pi n times the imaginary part of 1 plus n to the power of 1 over n. Since an exact solution for the MRB constant in terms of elementary functions seems elusive, let S equal the MRB constant equals the sum from n or k equals 1 to infinity of k to the 1 over k minus 1 over exp I pi k. Then we have the following non-trivial relation. As k goes to infinity, the asymptotic term of k to the 1 over k minus 1 equals the log of k over k. What about convergence? The previous surprisingly gives us that the sum of the asymptotic term k to the 1 over k minus 1 over exp I pi k as k goes to infinity plus the sum of k to the 1 over k minus log k over k minus 1 all over exp I k equals the sum k from 1 to infinity of k to the 1 over k over exp pi k. In essence, this equation shows that the original series can be split into a component of k to the 1 over k minus exp I pi k being summed, and the remainder of sum k equals 1 to infinity of k to the 1 over k minus the log of k over k minus 1 all over exp which equals, surprisingly, the sum from m equals 1 to infinity of negative 1 to the m over m factorial times the nth derivative of the Dirichlet eta function of m. And these absolutely convergent components together reconstruct the original series, converging to the sum of m from 1 including 1 of negative 1 to the m over m factorial times the nth derivative of eta m equals S that we called the MRB constant. Geometrically speaking, what are the MRB constant hypercubes? A hypercube, also known as an n-cube, where n is the number of dimensions, is a geometric figure that generalizes the concept of a square from 2 dimension or a cube from 3 dimension to a higher n dimension. Here are some key hypercubes. A segment with a hypervolume or length of 1, a square with a hypervolume or area of 2, a cube with a hypervolume or volume of 3, a 4 cube with hypervolume 4, a 5 cube with hypervolume 5, a 6 cube with hypervolume 6, and so on. Those hypercubes are special because they give the sides of each hypercube a length of n to the 1 over n. For instance, the length of the segment with hypervolume 1 is 1 to the 1 over 1, or 1, square 2 to the 1 over 2, 3 to the 1 over 3, the 4 cube 4 to the 1 over 4, and so on. What then do we do with these edge lengths? We sum them in an alternating series to get the MRB constant, CMRB, equals negative 1 plus the square root of 2 minus the cube root of 3 plus the fourth root of 4 minus the fifth root of 5 plus the sixth root of 6. There where you see 2 square root of 2, that's because the square root of 2 is the same as the fourth root of 4. Since every partial sum has a metric, the alternating sum of the sides, we can compare them. On a number line, we can go from n equals 1 down to negative 1 to the power of 1 over 1. And then at n equals 2, we can go up to negative 1 plus the square root of 2. And then at n equals 3, we can go down to negative 1 plus the square root of 2 minus the cube root of 3. And these alternate. If we were to extend the previous list plot, we see that if we go infinitely far, the segment that would be at infinity, so to speak, would represent the length of the MRB constant. That's negative 1 plus the square root of 2 minus the cube root of 3 plus the fourth root of 5 minus the sixth root of 6, and so on, all the way to the symbol infinity. The MRB constant can have implications and potential applications in various fields due to its connection with series, sums, combinatorial mathematics. Some potential areas where the MRB constant or similar mathematical concepts could be of interest include number theory and combinatorics. Understanding the properties of alternating sums and series can provide insights into number theory problems and combinatorial identities. Mathematical analysis, the study of convergent and divergent series such as those related to the MRB constant, can be important in the real analysis and study of infinite series. Computer science. Algorithms that deal with summation, especially those that alternate sign, may benefit from insights gained from studying the MRB constant. Physics and engineering. Series representations, like those related to the MRB constant, can sometimes be used to approximate solutions to differential equations or to model phenomena in physics and engineering. Finally, all of mathematical research. Pure mathematical research often explores constants like the MRB constant to better understand the properties of mathematical series and their implications in both theoretical and applied contexts. Well, I hope you've learned and enjoyed. Bye bye.